I come from a Bronze Age perspective and a statistic perspective, and when we talk about the flow of metal, mixing, recycling over the last 10 years in Oxford, we develop a range of statistical methods that can be applied to various kinds of metal composition, including coins. So I'm here to say that there are some fantastic tools that is just developed, and if you are interested, maybe we can do something together. From a and also another thing is I want to say that this person Pollard is really a key person that lead me into this field, because he was my PhD supervisor, and many of the research here actually is led by him, and I'm just a research assistant that helped him wrapping up very soon. So he's really the leading person. Coming from a Bronze Age perspective, I just want to quickly remind how important, how amazing metallurgy could be. It is one of the very early Eurasia phenomenon that, it is a complex technology, from mining to smelting to casting to polishing, and you need really a lot of social energy to do this. And by around 2000 BC and 1500 BC, the entire Eurasia is locked into this complex technology, and nobody can escape. And also, metal is not everywhere. It is not something that we can find out in the backyard, and people move because the metal deposits are located some in specific places. But here what I want to emphasize is that metal is probably the very first material that allows human beings to create some completely new form through recycling. So the recyclability of metal is really something that helps human beings to develop new understanding of the relationship between our society and something beyond. And recycling is not really, sometimes we often assume that recycling is an economic concern. We run out of metal, we recycle stuff. But actually it is quite not. In many other scenarios, that recycling can be regarded as an important clue to disentangle major historical, cultural, military events, like the very famous case that when the first emperor of China, Qin Shi Huang, unified whole China, and he recycled all the weapons and made 12 gigantic figures standing in front of his court and say, "Hey guys, we step into a peaceful era now. No military practice needed." And also, when we come to the later historical period, when temple economy and a state economy clash with one another, and people try to demolish temple economy, demolish Buddhism, and try to recycle the Buddhist statues into coins and increase the state economy, pay the soldiers, etc., etc. So these are the major events that are deeply rooted in the activities of recycling or mixing metals together. So over COVID, my colleague and I organized a special issue about rethinking recycling in the past on archaeometry, and in this special issue, we invited a number of scholars to discuss recycling. How can we detect recycling in various materials like glass, glaze, metal, copper, gold, iron, silver, etc., etc. So there are several methods. They are quite interesting statistic or other methods you can allow you to find out recycling in the past. If we go to Bronze Age China, and one of the important things for Bronze Age China is the scale of production, exemplified by bronzes here. And when I present this guy, this is one of the largest steel vessel made in early Bronze Age China. That is called the Late Shang Dynasty, 100 BCE to 1100 BCE. And this guy is nearly a ton of metal. This is just one single ritual vessel. And if you want to make this guy, and you need to process 100 tons of metal, roughly speaking. And when I present this to my colleagues in Oxford, one guy says that, did you miss a point here? Is it 800 or 832 or 883? And this is something we learned from our primary school, that because, I mean, then my colleagues say that if you recycle all the bronze weapons from early Bronze Age Britain, that is equal to this single piece. So the share of metal is really important. And one of the important things that bothered the late Shang kings and people is that many major bronze production happened here, and this is a distribution of coppers in China. Actually, this is just the poorest region of this copper deposit. The major deposits of copper are here, and here, here, and here. So basically, there's a clear imbalance between the raw materials and the production. And so how can we get enough metal to sustain the large-scale metal production? And so we use the last capital city of the Shang dynasty called Anyang as a case study. And in Anyang, one of the most important social feature is a strict hierarchy, and the people on the top elite can have access to a variety of exotic things, materials, objects, whereas people on the lower elite or ordinary people have a very ordinary, limited access to materials. Like this is one of the king's tomb in Anyang, and you can see this is quite deep. And if you go deep, it's here, and this is one of the bronzes, like here. And this tomb is about 100 square meters. 100 square meters. 100 square meters. And all of the king's tombs are looted. And the only intact royal family tomb is called the Fu Hao, one of the consort of the King Wu Ding. And in her tomb, people found jade, people found bronzes, and the overall amount of bronze is about 1.6 ton of metal. So this is just one top elite at Anyang, and there are hundreds of them. And if you look at the lower elite or ordinary people's life, this is one section of Anyang, and each dot represents one tomb. And in this dot, they probably have like 1 or 2 pieces of bronze or 1 or 2 pieces of pottery. So how can we detect mixing and recycling? And there are several ways we discovered based on the alloying data, lead isotopic data, and the trace element data. For Chinese data, I realized that alloying data and lead isotopic data for Chinese Bronze Age are most useful for detecting mixing and recycling. If a group of objects present this kind of primary alloying practice, we call it like this is the tin distribution or lead distribution, as we discussed. Tin and lead are the major alloying components throughout Chinese Bronze Age, even down to the coinage period. And this is the percentage of metal assemblage. You can see that the majority of tin is averaged around, for example, a specific value. It looks like a normal distribution. This means that the recipe, there is a targeted recipe that people have to use pure copper and add pure tin and pure lead into the pure copper, or with relatively pure, higher purity to control the alloying recipe in the end. And this is a case of the top elite metal assemblage at Anyang. And if you look at the low elite metal assemblage, we sometimes call it a skew pattern, which means that the majority of objects contain tin or lead and one type of alloying less than 5-6%, because when you recycle stuff, you lose tin and a chunk of tin percentage and some level of copper as well. So your alloying composition goes a bit leftwards. And also, I mean, when you do recycling, another assumption which I couldn't prove is that it's through dilution with copper. So copper is added to the previous objects. And if we look at a bigger picture and we assemble all the data we have at the moment, we divide them into different phases of Anyang and the top elite and low elite. What you can say here is that the variation of tin and lead of the top elite metal assemblage is much lower than that of the lower elite metal assemblage, like this. This is another way of showing this kind of targeted alloying recipe that people use quite a good quality of tin, lead, and copper to create this bronze objects. To put it in another way, if you recycle or mix broken objects together, although you can tell that by naked eyes, you can tell that this object probably contains like 10% tin or lead. You can't calculate it precisely like this kind of primary alloying pattern. And also, if we zoom out of Anyang, there are many other important sites between from Yellow River to Yangtze River. And what we can say is that, especially for tin, what we can say that the variation of tin of the top elite people here is still a much lower or precisely controlled than other important metal assemblage outside Anyang during the same period. And this is a lead, a variation of lead. And also we can have another piece of evidence from trace element. And here, if we compare the trace elements such as arsenic, zinc, silver, antimony, etc., you can see that the impurity pattern of the top elite people, Fuhao, at M1046, is much lower than the lower elite metal assemblage, which means that their copper is highly refined. So it echoes for top elite metal assemblage, the materials needs to be in a very higher purity, and people treat their materials very, very carefully. So based on this, if we incorporate the element of mixing and recycling into the social hierarchy, what we argue is that if a group of materials, either in terms of pure, low quality, high quality ingots or broken objects, scraps or whatever, into Anyang bronze workshop, there is a very sophisticated system that allows you to separate the top elite materials and low elite materials. Top elite materials with higher purity would go to the high line production that create high elite or top elite metal assemblage like bronze ritual vessels, and the low elite low quality materials would go through this low line and create some kind of like low elite metal assemblage. It is likely that the top elite metal object end up into the lower elite tombs because of gift, because of rewarding, etc., etc. But I haven't seen any case that the lower elite objects end up in the high elite tombs. One of the key message is that people in the workshop, they really understand what their patrons, their customers, I have to say, because many of these bronze ritual vessels or bronze objects have inscriptions, and you know exactly which family, which specific person you are produce objects. So this is the alloying. This is the way to detect recycling through alloying, and we have another way to look at the alloying through combination of lead isotopes and lead concentration. And if mathematically, if we plot the inverse of the lead concentration with one of the lead isotopes, and if we got this kind of linear pattern, we know that all the dots, all the objects sit on this linear pattern are the result of mixing two components together. So we can demonstrate this by various mathematical ways. I'm not going to bother this with you. And if you are really interested, we publish in our book that can be freely downloaded online. And the specific case study here is the interaction between Central China and the Eurasia steppe. And the intermediate zone is called the arc that sits in between. And what we can say here is China is very good at making this kind of bronze ritual vessels, and they're agricultural people, which means that they settle in one area and grow their crops. As you go north, you enter into this kind of mixed area where both animal herders like horse people as well as agricultural people can both live together. However, I mean, this area is the arc is in many periods dominated by the animal herders, and they are not they have a much higher mobility, and they do not really like the bronze ritual vessels. And their style, their bronze objects are mainly belt hooks, single blade knives, and horse gears, etc., etc. And if we plot the objects here, we can see this kind of mixing line, which means that this area uses a lot of mixing and recycling. And given the fact that this area is also dominated by leaded bronze, which is like Central China, we think that probably the way they access metal is through recycling of bronze ritual vessels from the south into north. And also we have a quick project, a new project to look at this kind of north-south interaction. Since metal goes into south, end up into this kind of recycled materials, what is the other side of the exchange? And the hypothesis is horses. We think that horses is important for Central China, and horses move from north to south. And this is the mutual direction between horses and metal that underpinned the social diversity or the mutual exchange between these areas. And our project is going to extend this idea to Mongolia, and to see how much we can apply this idea to a wider area. And another thing, and another way to look at another small case study that we discovered is with gold. As we all know, gold is a very precious material, and it can be often recycled. However, to be honest, we don't so far in scientific analysis has no way to detect like which gold is for which for two reasons. One is that we haven't found a single physical feature under microscope that if it contains this kind of physical feature, it is recycled. The second thing for gold is that nobody allows you sampling. So so we have to do this kind of non-invasive analysis. And I mean, it's just very lucky that we found this kind of object which contains a lot of copper and a lot of how do you say it, tin and lead. And if you if you remove gold and turn the copper tin lead, into a regional ratio, you can say it is similar to the bronze rich vessel. So we think that there is a kind of practice that gold and leaded bronze or bronze materials, either in forms of finished objects or in forms of like ingot mixed together. And if anybody find a piece of gold that contains both tin, lead, copper, please let me know, and then we can think about this. Okay, so enough about Chinese rich vessels or Bronze Age, and a little bit of coin. This is mainly Mark Pollard's idea, and in the beginning I have to say I didn't accept that, but the more he talked to me, I think the more smart, a very clever idea. What he discovered actually is that if you plot the wonderful data set created by Joe and Helen, you can see, for the Chinese coin, you can see two patterns here. One pattern is this kind of linear pattern, and this is a kind of random group together. It's a round circle here, and basically focus on this material, this line here. In the beginning, I thought this is nothing because China has a copper, tin, lead as the three major elements, and if you add them together, it is 100%, roughly speaking, right? So it is called sum unit problem. If you plot them in a XY plot, inevitably it will show you a linear pattern somehow. But then Mark got this idea that wait, if you plot them together, they show you some kind of correlation that means like there's something inside. For example, for this one, I mean, copper and lead are negative correlation, which means that when you have a higher concentration of copper, lead becomes lower, or vice versa. But copper and tin have a quite clear positive correlation, which means that if you've got a higher amount of copper, you have a higher amount of tin. And if you just like the creating full house, like everything is independently added, it means that copper and tin should be a negative correlation. But here it is a positive correlation. Then he did something quite clever that he thinks that probably it is not a pure copper, pure tin, pure lead are combined together. It is another layer which is pre-alloying stuff, which means that you first create pre-alloying with, for example, in this case, we propose 85% copper, 80% copper plus 15% tin and plus 5% lead as a pre-alloy. And another group is 50% copper, 50% lead as another group. And then you add them together. And only by this way that you can create this kind of line, mixing line that fits our data. And we try all different ratios, other different ratios like 60% copper, 70% copper, and you can basically simulate them. So this is and only this way fits the data very well. So this is a quite interesting thing. And then we further, this is also Mark Pollard's idea. I think this is brilliant because I mean the very earliest textual evidence for Chinese alloying is this table. This table says that there are two elements. One is called gold, or Ji in Chinese, which is actually not gold, probably copper or copper alloy, and the other is called Xi or tin, but actually it is probably not tin. And by creating, by mixing these two elements, and we can create all sorts of different types of bronzes, like bronze-rich vessel, etc., etc. But then the question is that if all the Chinese pieces contain copper, tin, and lead, three types of elements, and if you only use two types of elements, you cannot create a three ternary alloying stuff. Then, but what we can say here is that if you use this kind of pre-alloying components, which means that 85% copper, 80% copper, 15% tin, and 5% lead, plus 50% copper, 50% lead, you can create this kind of ternary alloying. So, but at the moment, we do not have any evidence to say that Jin and Xi, these two ancient characters or elements, are corresponding to the pre-alloyings we proposed. And so I think that there is something that we can connect coinage data and this kind of alloying practice recorded in ancient text together. But the case in here we are missing is lead isotopic analysis and trace element. Here we only got the alloying data to examine this. And another case study that I'm involved is the silver sciences. This is not led by me. This is led by one of my friends in Oxford. She's now in Beijing Normal University, and she's a Ming and Qing expert. When she told me that, I mean, a lot of Spanish coins or Potosi silver moved into China, and she wants to study that, then I said that maybe we can look at their composition to track the flow of metal in this area. But we do not have many data. We collect all the data from the literature sources, and what we can say is that the concentration of silver in Chinese silver sciences is pretty high. It's like Tang, Jin, and Song, Yuan, Ming, and Qing. And if you compare the Ming China and the Mexico Potosi data or Qing China, and you can see there is a kind of a gap between these two data sets, which means that if you just move the silvers from Potosi to China, it means that in each transaction, each silver, you kind of like miss 5% silver in it, and maybe this is silver, this is copper, this is better. So then she asked me the question that how can you tell, like just by naked eyes, how can you tell this ingot or this coin contain like 92% silver and this ingot contain like 98% silver? How can you tell it? I said, I don't know. I do not know. And if it is untrained pair of eyes, it's probably by color, things like that. And so that is really something I want to ask the expert here. And during COVID, we just get bored, and we do our own analysis, and we carried out a series of simulation experiments to create like a silver with 3% copper, 6% copper up to 25% copper, and silver with 3% lead, 6% lead up to 25% lead, I think. And then we measure the color difference, the color of these simulated blocks by what's the word, chromometric data. And then I did a Monte Carlo iteration. Say that two discoveries. One is that the change of color by copper on silver slices is much bigger than the lead, which is quite clear from the ingots. And also another thing is that if you compare a piece of a Spanish coin or Mexico coin with a Chinese silver coin, you can see that actually there's 80% chance that you can tell the difference just by naked eyes. No, you don't need to be trained as an expert, and that is something we discovered. So basically, I think there's something happening when the Potosi or Mexico silver moved into China, and the Chinese people must be aware of that. Their silver percentage is lower than those within China, and there's something happening there. So my colleague is trying very hard to look at to find out literature to see what is happening between this kind of border activities. And if any of you know any kind of like quality check or quality improvement at the border activity, please let me know. I'm really appreciate. So this is the end of my talk. Thank you very much.